Hi everybody, this is Miss McClellan here to go over IM2 Notes 3.1.1 with you. How can I represent it using an area model? In previous courses, we studied probability, which is a measure of chance that a particular event will occur. In this section, we will solve probability problems that require us to analyze more complicated situations of chance. Our learning goal: I will be able to use an area model to represent sample space for situations of chance and use that model to calculate probabilities. Period. First problem, 3.1. It's in the genes. Assume that half the US population can bend their thumbs backwards and that half can roll their tongues, and that these genes are independent, meaning that having one of the genes does not impact whether or not you can have the other. And randomly distributed, meaning that across everybody in the United States population, it's not possible to pinpoint which people will have which genes just based on where they are. Let's complete the table below to organize the sample space. Okay, so this is an area model. To do an area model, you multiply the edges to get the center. This is 1/2 times 1/2, which equals 1/4. This one is also 1/2 times 1/2 equals 1/4. They're actually all the same, which is not always, or even really often, the case. Now, according to the table, what is the probability that a randomly selected person from the United States has both of these special traits? Oh, this is what this traits look like. This is what it looks like to be able to bend your thumb. And this is what it looks like to be able to roll your tongue. Some of us can do it and some of us cannot. All right, back to this. So, oopsie, hold on one sec. According to the table, which is the probability that a randomly selected person from the US has both special traits? That means yes, yes. And it happens right here. Yes, they can bend their thumb, and yes, they can roll their tongue. And that is the probability of both traits. And it equals 1/4. Also, according to this table, what is the probability that a person has only one of these traits? Probability just 1. So we've got a couple combinations. That could be yes, no. It could be this box right here. I'll do it in pink. Only one trait in this box. And only one trait in this box. So that equals either of those things happening. You'd add them together. 1/4 plus 1/4 is 1/2. Now, if you prefer, students, you can always deal with probability as a decimal. Decimals are so useful because it makes it so that everything is in the same form and can be added and subtracted and multiplied and divided without knowing any special tricks. Although fractions are beautiful. Problem 3-2, using an area model. One way to represent a sample space that has outcomes that are not equally likely, in the last problem, the outcomes were equally likely because the probability of yes and no were equal for each trait. So when they're not equally likely, we can use a probability area model. An area model uses a large square with an area of 1. I claim this was also an area model. Look, this has an area of 1. 1/4 plus 1/4 plus 1/4 plus 1/4 equals 1. The square is subdivided into smaller pieces to represent all possible outcomes in the sample space. The area of each outcome is the probability that the outcome will occur. For example, if 1/4 of the US population can bend their thumbs back, then the column representing this ability should only take up 1/4 of the square's width. And we have that here. Let's look at part A. How can the diagram be completed to show that 7/10 of the US can roll their tongue? Okay, let me see. 1, 2, 3, 4, 5, 6, 7. 7/10 of them can do it. So I'd say right here, yes and no. 7/10. And the rest is 3/10. 7/10 yes, 3/10 no. We created 2 rows. The first row is yes, the second row is no, to represent that probability. Now, the proportion of people, the portion of the probability model, the probability area model, representing people with both special traits, is a rectangle with a width of 1/4 and a height of 7/10. Let's find that. That's right here. Width is 1/4, height is 7/10. What's the area of that rectangle? Well, that's going to be 1/4 times 7/10 is 7/40, which is 0.175. And it is indeed 7/40. There are 7 in the box out of a total of 40. What does the area of the rectangle with a width of 1/4 and a height of 7/10 represent in our area model? Well, it represents the probability that someone can both roll their tongue and bend their thumb. Period. Part C. What is the probability that a randomly selected person can roll his or her tongue but not bend his or her? This should just say there. I'll change it in the notes. See? Thumb back. Show how you got this probability. Well, let's see. This is the probability that can roll tongue and can not bend thumb. And it equals, which rectangle is that? Cannot bend thumb and can roll tongue. So that's this one. That is 3/4 by 7/10, which is 21/40. And that's 0.525. There we go. The probability of something corresponds to the area of the section of the area model represented by that probability. 3-4, shipwrecked. Zach and Nick, who are from Vermont, are shipwrecked on a desert island. Zach has been injured and is losing blood rapidly, and Nick is the only person around to give him a transfusion. Most populations can be classified into 4 blood types: O, A, B, and AB. If you've participated in a blood drive, you probably know your blood type. Not everybody has. Anyway, in Vermont, about 45% of people have type O blood. 40 have type A blood, 11% type B, and 4% type AB. What are other ways in which people's blood can differ? There are other ways in which people's blood can differ, but this problem only considers these 4 blood types. So first we have to complete the area model. And if we're trying to multiply percents, we need to use the decimal version. So this is going to be 0.45. This is 0.4. This is 0.11. This is 0.04. Similarly, 0.45, 0.4, 0.11, 0.04. Now to find all of these, you perform multiplication. So this box right here, I'll zoom in, is 0.45 times 0.45, which equals, if I don't have any mistakes, and I might, 0.2025. This box is 0.4 times 0.45. This box is going to be 0.11 times 0.45. This box will be 0.04 times 0.45. This box will be 0.45 times 0.4. This one will be 0.4 times 0.4. This one will be 0.11 times 0.4. This one will be 0.04 times 0.4. This one will be 0.45 times 0.11. 0.4 times 0.11. 0.11 times 0.11. 0.04 times 0.4. 0.04 times 0.45. 0.4 times 0.04. 0.11 times 0.04. 0.04 times 0.04. Put my equal signs in. You don't have to show this step. You could just show the results. But I want you to understand what it is I'm doing. I don't just want numbers to appear on your screen and for you to copy them. So hopefully this helps. Okay. We've got, I'll do the diagonal first, 0.16, 0.0121, 0.0016. We've got 0.18, 0.044, 0.0044, 0.0495, 0.016, 0.018, 0.18, 0.044, 0.0044, 0.0495, 0.016, and 0.018. I'll make that 8 meter. And that's our area model. Now we can use it. Okay, what is the probability that Zach and Nick have the same blood type? So that would be the probability of us having OO or AA or BB or AB. Where do those happen? OO is right here. AA is here. I want more colors. BB, that's right here. And AB, that's right here. And that probability is all of this total probability is all of those little probabilities put together with addition. 0.2025 plus 0.16 plus 0.0121 plus 0.0016. And if you add all that up, you get 0.3762. And that seems like it's the final answer because technically probability is a number between 0 and 1. So that's it. If we had asked for the percent, well, this isn't a percent, this is a probability. So it should be a number between 0 and 1. That's why it's not 37.62%, but it is 0.3762 as a probability. Okay, so luckily, two people do not have to have the same blood type for the receiver of blood to survive a transfusion. Other combinations will also work, as shown in the diagram. We don't have a diagram, so I'll take that out of the notes. Assuming that their blood is compatible in other ways, a donor with type O can donate to receivers with OA, B, or AB, while a donor with type A can donate to receivers with A or AB. Well, a donor with B can donate to B or AB, and AB can only donate to AB. So let's find the probability that Nick can save Zach's life. So what's the probability that Nick can give Zach his blood? Ugh. Anyway, so one way for that to happen would be if they had the same blood type. So that's the probability, same blood type. Plus the probability that Nick has type O plus the probability that Nick has A or B and Zach is AB. Let's see if we can find these. I think this is going to overcount it, but we'll deal with that in just a second. So let's look. The probability that they have the same blood type, we already did that. That is 0.3762. Plus the probability that Nick has type O. Let's see. That's 0.45. Plus the probability that Nick has A or B, and Zach is AB. So that I'm going to have to do a little bit of more work for. So let's see. Nick has A or B, and Zach is AB. So Nick could be A or B, and Zach must be AB. So it's either of these. Okay. That's plus 0.016 plus 0.0044. But this is not going to be completely correct because I think I'm going to be double counting some things. Let's take a look at that now. 0.3762 is the probability that they have the same blood type, and that could happen in any of these diagonal pieces. Okay. The probability that Nick has type O is 0.45, and that could happen in any of these pieces. So if I were to add all of these up, I'd be adding one piece twice because I can see that I've got a double piece right there. So I should subtract that out. Otherwise, I'll overcount. So I need to subtract 0.0205. Okay, let's see what this equals. This whole thing equals, I'm going to put it in my calculator. Okay, we got it. It's 0.8261. That's our probability. I'd say that's a pretty high chance. I mean, I'd like it to be 100% that they could both survive, but at least it's not 50-50. Okay, 3-5. We made a really important assumption in problem 3-4 when we made a probability area model multiplied by the probabilities. Blood type is impacted by genetic inheritance. How could the following impact the possible outcomes? For example, what if Zach and Nick were related to each other? Well, if they were related, then they are not random, then their probabilities are not independent. So an area model would not be reliable. Knowing, for example, Zach's blood type would impact the possible blood types for Nick. We said that area models had to be between independent events, so that would be a big problem. In order for a probability area model to give an accurate theoretical probabilities, the outcomes must be independent. Period. Okay, we keep going. Last but not least. All right, here we have notes and a word bank. Here we go. A compound event in probability refers to an event that consists of two or more simple events. In other words, it is an event that combines multiple individual outcomes. An outcome in probability refers to a possible result of an experiment or trial. For example, suppose you spin the spinners shown. If you spin spinner 1 first, then the possible outcomes are, okay, here are the spinners. Spinning 1 first means that the first letter would come from spinner 1. So we're either going to have IT or UT or AT. Oops. Or we're going to have IF or UF or AF. The probabilities for any event, the probability for an event is between 0 and 1. If you add up all the probabilities of all the possible outcomes for an event, they will sum to 1. When considering exactly two compound events that are independent, an area model can be used to calculate probabilities of outcomes. Independence in probability means that the occurrence of one event does not affect the probability of the occurrence of another event. For instance, flipping a coin and getting heads does not change the probability of rolling a 3 on a die. If the probability is 0, if the probability is 0, then the event will not happen. If the probability is 1, then the event will definitely happen. If an area model In an area model, a rectangle with a total area A equals 1 represents a situation. The areas of the parts are outcomes, so they add to 1. All right, that's the end of the notes for today. I hope you found them useful, and I'll see you next time. Thanks for following along.